or not day 1, day 4 notes. So today we're going to talk about solution concentration. Like I said, today's only 5 slides. It's nothing that bad, to be honest. So solution concentration. We're talking about how much stuff, I guess you could say, is in a solution. So how much of a solid is in solution. An example of this is if we say we have something that is 10% NaCl. What that is saying is that there is 10 grams of NaCl in every 100 grams of, and now this is where we really have to be able to differentiate between 3 different words. It is 10 grams of NaCl in every 100 grams of solution. Please note, solution is everything inside of that beaker. So everything in that beaker is your solution. So that means when I have 10 grams of NaCl and 100 grams of solution, how many grams of that is water? It would be 90 grams of this water, because our solute is our NaCl. So 10 grams of this is our NaCl. The remaining 90 grams is going to be water, because there's 10 grams of NaCl and 100 grams of solution. So when my beaker itself has 100 grams of stuff in it, 10 grams of it is NaCl, 90 grams of it is H2O. So solution concentration, to solve for this, you take your grams of solute divided by your grams of solution times 100. I think that's probably pretty straightforward for most of you. You're just solving for a percent of something. Another way to look at it, and the way I would recommend looking at it, is grams of solute divided by grams of solute plus grams of solvent. So that way you're thinking about your solute, your salt, or whatever you're dumping into the water, and your solvent or your water. You're keeping those separate because some questions are going to ask you to solve for how much solvent you would need, or how many grams of solute you would need. And it's much easier for students when you keep those separate. It's much easier when you keep those separated. So to help break this up for you, solute is salt, solvent is your water, and then your solution is going to be everything that is inside of the beaker, just if you need a nice visual. So here's kind of an example problem. 32 grams of salt are dissolved in 120 grams of water. What is the solution concentration as a percent of salt? Well, a lot of students start off doing is they're just like, oh, I'll take 32 grams of NaCl divided by 120 grams of water, and I'm just going to take that times 100. Well, the issue is if I need to know what percent my NaCl is, I need to count my NaCl as part of the weight. So you actually cannot do that, because you need there's 152 grams of solution. The total mass in that beaker is going to be 152 grams, because solution is your grams of solute plus your grams of solvent. Kind of another way that you can think about this is because some students, again, you get a little confused. Let's say I'm trying to solve for my percent of Skittles. So I go through and I'm like, all right, I have 4 blue Skittles, and I have, I'll just do this, and I have 7 red Skittles. Well, what's my percent of blue Skittles? I don't think many of you would go and take your 4 blue Skittles and divide that by your 7 red Skittles and multiply by 100. You're not going to do that. You have to take it per your entire sample amount of Skittles. So you have to take your 4 blue Skittles divided by your 11 total Skittles, and then multiply by 100. So you always need to take it per your entire sample amount. And a couple other ways we can look at this. Sometimes talking about something in percent or parts per 100 isn't enough. Like when we talk about carbon dioxide in the air, we generally talk about it, particles, we talk about it in parts per million or parts per billion. The only difference here, because students make this way more challenging than it needs to be, the only difference here is now instead of multiplying by 100, which when we do this, this could also be called parts per 100 because we're multiplying by 100 here. Parts per million is the exact same thing, except for now we're going to multiply, instead of multiplying by 100, we're going to multiply by 1 million. That's the only difference. Or if we talk about ppb, parts per billion, the only difference here is now we're going to multiply by I have to count. Did I even do that right? Yeah, it's good. We have to multiply by 1 billion. So please note those numbers are the same. And the reason that we do this is if we say that the air contains 396 parts per million of CO2, that means for every million particles that are in the air, whether it's nitrogen or oxygen or methane or whatever, for every for every million particles in the air, 396 of them are CO2. And the reason that we do that is because if we talked about this as parts per 100, if I said for every 100 particles that are in the air, that would mean that I would be saying I have 0.000396 particles of CO2. Well, that's a really inconvenient way of saying it. So that's why we talk about things in parts per million, and this is actually one of the ways that they have determined that humans are causing a huge issue with global warming and with CO2 productions, because they'll go to places like the Arctic and they'll dig way, way, way deep into an iceberg, and they will take out a chunk of the iceberg that is from 150,000 years ago or so, and they will determine the concentration of CO2 in that versus the concentration of CO2 in an outer part of the iceberg, and they'll compare and see that our CO2 concentrations have increased greatly. So that's just kind of an example for you. But that is why we talk about things in parts per million or parts per billion, because sometimes 100 particles is not enough to compare it. So if we have 15 grams of sucrose, which is also known as table sugar, is dissolved in 150 grams of water, what is the concentration in parts per 100? I should blank these out so you guys don't automatically have the answers. Again, you need to take 15 grams divided by 165 grams of, again, the word here is solution. This is going to be our 15 grams of sugar plus our 150 grams of H2O. Times 100, so that means that of my sugar it is 9.1% or 9.1 parts per 100. Or we can talk about, given a 25% concentration solution of NaCl, determine how many particles per million of solute there are. And this is where, honestly, you kind of do the same process we learned yesterday. Well, if it's a 25% concentration, that's the same as 25 parts of NaCl per 100 parts of solution. So to solve for that, you're just going to take X parts, some sort of parts of NaCl, and now we want to solve it per million parts of solution. And you get an answer of 250,000 parts of NaCl. So it's just 25%. What's 25% of a million? 250,000. Any questions on stuff so far? Okay. So let's have you try this one. And this is meant to be a challenge problem. If we want a 35% concentration of an acidic solution, how much water must be added to 10 grams of acetic acid? So first go through and solve. What is your solute? What is your solvent? And what would your solution consist of? And then go back in your notes. You only have 4 slides to choose from, and figure out what equation are you going to use. I'm going to walk around and see if any of you can figure this out. This is meant to be a challenge problem. This is also question number 5 from your homework for tonight, which is assignment 6.3. But I'm going to give you a minute or 2 to work through this one. If you want to work with the person next to you, you are welcome to. So I think about 4 of you had it correct, or were on the right track. So if we go through and label this, what is my solute? What is it that I'm dissolving? Yeah, we're dissolving our acetic acid, so that is going to be my solute, 10 grams of acetic acid. Okay, what is my solvent? Pretty much always water. Do we know how many grams of water we have? No, because that's what we're solving for, how much water. So we have some sort of X grams of H2O. And then our solution is going to be 10 grams of acetic acid plus X grams of H2O. So what equation are we going to use? Well, you kind of have 2 different options that are really the same thing. We have our equation, if we jump back a few slides, we have this equation. Solution concentration, which is some sort of percent, is equal to grams of solute divided by grams of solute plus solvent times 100. Oh. So we go through this. What equation will we use? We are going to use our grams of solute divided by grams of solutes plus grams of solvent times 100 is equal to some sort of percent. What are we solving for in this case? We're solving for our solvent. And this is where most of you got tripped up. So a lot of you are on the right track, but a lot of you solved for this entire bottom part. And that's why I warned against that and wanted you to make sure you follow your labels. Because we already learned our grams of solvent, or our grams of solute. So I don't want to solve for the entire denominator. I only want to solve for my grams of solvent. I only want to solve for my grams of water. So if we go through and start plugging this in, it tells us that we have 35%, or we desire 35% concentration. You have to remember to have your times 100 in here, because that's part of the equation. Or you could also ignore the times 100, but then you need to take this out of percent form and leave it as 0.35. I'm going to simply recommend leave the 100 in there. So now we go through and plug in our values. Well, we know that we have 10 grams of acetic acid, which is our solute, divided by, and again, we have grams of solute. We have this exact same variable here again. So we need to plug in the same thing. And we're going to have 10 grams of acetic acid plus X grams of H2O, because that's what we're solving for. And some of you got this far and then start getting a little tripped up on the math. First thing I'm going to recommend that you do is just divide both sides by 100. Divide by 100, so those cancel out. Divide by 100. And now you're going to have your 10 grams of AA divided by 10 grams, X grams of H2O is equal to 0.35. Now is where it gets a little bit tougher, because we can't just multiply by 10 grams of AA, and we can't just cross these numbers out because we have addition here. So that's not following our proper rules of math. So what we actually have to do in this case, I don't know where this came from. We're just going to hide it. Now what we actually have to do is multiply by our denominator. So I'm going to take and I'm going to multiply by 10 grams of AA plus X grams of H2O. Now that will cancel out with this. We have to multiply this whole thing through. And we're going to have 10 grams of AA plus our X grams of water again. This ends up being quite the problem. And now we can rewrite this thing, and what we have to do is multiply our 0.35 through. So we're now going to have 10 grams of AA. And I know there are shortcuts to doing this, but I'm taking the long way, so hopefully everybody can follow, is equal to, and 0.35 times 10 is going to give us 3.5 grams of AA plus 0.35 X grams of H2O. Alright, now this problem's looking a little bit easier. We can subtract 3.5 grams of AA from each side, and we're going to get 6.5 grams of AA is equal to 0.35 X grams of H2O. We're getting there. And now the last thing that we need to do, just divide by 0.35. So we divide by 0.35, divide by 0.35, and you are going to get, I actually don't remember the answer to this one. What is it? 18.57, that would make sense. And you get an answer of 18.57 grams oh, you know what? Our units canceled out here. When we subtracted grams of this, when we took 10.5 minus that, units should cancel out, and you get 18.57 grams of H2O. Ends up being quite the work, and that is why I said it's a challenge problem. Yes, there are shortcuts you could have taken back at this step up here, or this one down here. I just kind of want to take the long way, so hopefully everybody can follow the algebra. That is an example of one of the harder problems that you would see. But that is why you have to take it slowly. Don't try and fly through this whole thing. For those of you that got this one correct, very nice work. But it was meant to be more challenging. And that is what I'm going to recommend. The rest of the class time is yours. Please finish up the lab. I would say let's work on that first. And then your homework for tomorrow is assignment 6.3. I would ask that you please remain in your desks. If you want to work together, you may. But let's use this as good, quiet work time.